Lecture number 3, work and energy. We have three questions, work, energy and power. And the second question, we will study kinetic and potential energy. And final question, law of conservation of energy. And the first question, work, energy and power. And here this is a figure. If a body moves through a displacement S while a constant force action on on it is the same direction in here. This is displacement direction, and here this is direction of the action force. The work done by the force on the body is work equal force multiplied by displacement. We define the work done by the constant force under this as a product of force magnitude force and the displacement magnitude S. In here, this is formula constant force in direction of straight line displacement. And the unit of the work, joule. And 1 joule equal 1 Newton multiplied by 1 meter. And the next, car moves through displacement as a while as a constant force act on the angle to the displacement. In here, this is direction of the force act on the and here on the body. And the end on the force one force projection of the force and parallel of x axis, and here perpendicular. But in perpendicular force and does not work on a car in here, but in here, and perpendicular force equal force multiplied by sinus alpha. And here, this is F perpendicular, F multiplied by cosine theta. In here, this is triangle. And only F parallel force does work on the car. In here, this is on the car, and work equal F parallel force multiplied by displacement. And we know, and parallel force will be equal and force multiplied by cosine alpha, and replace. And then here in final formula, in here this is work. And this is formula and the constant force straight line displacement. And here constant force straight line displacement in here. The next, a constant force can do positive, negative, or their work depending on the angle between and force and the displacement. This is three type and direction. In here, this is column direction of force or force component in here, and situation, and this is figure and situation. And we in here the final column, in here force diagram. Maybe we take the part number A. Force has a component in direction of displacement. We know work is a positive will be, and work equal F multiplied by cosine alpha multiplied by displacement. This is direction of the force, and here this is angle between and projection as x axis. Okay, and here this is displacement, two position in here. And force diagram, we know, and perpendicular doesn't work on the car, and parallel force on the in here, and force multiplied by cosinus alpha. In here, this is work as a positive. And part number B, and here, force has a component opposite direction of the displacement. This is and displacement. but and force acting on the body and opposite direction of the here of this displacement. Work will be the negative because f multiplied by cosine alpha is a negative, and for and angle and here this is between 90 degree and 80 180 degree here. And work formula of the work, it's 2 f cosine stat multiplied by s. In here for the diagram following, this is example, and perpendicular force and parallel force, and this is direction of the force, this opposite direction of the displacement. If we're using, and here this is maybe 90 degree and 180 degree. And part number C, force F, or force component F perpendicular is the perpendicular to direction of displacement. The force or force component does no work on the object in here because an angle equal 90 degree, and does no work on the object in here. And the next term, physical term, and power. We know, and how fast the work is done, we use the concept of power. The average power is defined as the average time rate of work done, W, during at the time interval delta T. Average power and work divided by time interval. And we know, and the system international unit of power is called watt. 1 watt equal in the formula joule divided by second. It may be and replace kilogram multiplied by square meter divided by cube second. And maybe and instantaneous power. Instantaneous power is limiting value, and delta T limit average power, and limit delta T approaches 0, and average power, and will be equal the first derived work of the time. The first derived. Using definition of the work and velocity in here, and work equal the first derived power equal the first derived work and divided by time, and work we know formula of the work force multiplied by the air, and using and the air divided by time will be velocity, and final formula of the work. Final formula of the instantaneous power will be force multiplied by velocity. Force multiplied by velocity. In another unit of the work, but the watt. On the watt is a kilowatt hour, and kilowatt equal to work done by an engine of the power of the kilowatt during 1 hour. We know 1 kilowatt and kilo in here, this is prefix 1000 watt divided by hour and divided by our multiplied by in here 3600 seconds, and will be work equal 1 kilowatts multiplied by hour equal in here 3.6 multiplied by 10 power 6 joule in here. And the second question, kinetic and potential energy. We know, and kinetic energy this is energy of the motion. And consider a particle which moves under the action of a force F. We now, and the definition of the work may be transformed as follow. We know, and work equal force multiplied by displacement. But we're using, and the force, this is action, force on the body, and using replace and Newton's second law and MA multiplied by ds in here. And this is, and mass, we know, and here this is acceleration. Acceleration show you the changing velocity, and I using an instantaneous acceleration. And here this is velocity in here, this is velocity, but we know, and the velocity is the first derived position of the time. And here this is the s divided by the t, and here this is v, will be v. And the final formula in here, this is mass multiplied by velocity multiplied by dv. But in here, this is elementary work. And final formula in here, and v multiplied by dv, and v and v square in here, m divided by 2. In here, v multiplied by dv will be v squared divided by 2, and m divided by 2 dv squared. And in here, this is elementary work and equal elementary kinetic energy. But and work done by the force during infinite displacement along the trajectory from point A, maybe from point A to point B, maybe expresses the equation. And work equal and integral from A to B, in here, from A to B, and replace and element work in here, this is, and mv squared divided by 2, and integral, and will be, and changing kinetic energy, and from B point, and minus kinetic energy following and A point. And final formula in here, this is work equal changing kinetic energy. And here this is the formula. And here this is formula work energy theory. The quantity kinetic energy 1 divided by 2 mv square is called the kinetic energy of the particle. And the kinetic energy may be in the second formula, and using, and we know formula of the momentum formula of the momentum, and mass multiplied by velocity, and replace, and following and final formula kinetic energy, and depending of the momentum, and the second formula in here, this is second formula kinetic energy of the particle. And here this is kinetic energy depending of the momentum. And and here, and we by means of kinetic energy, work may be expressed as a difference value of kinetic energy and the end and beginning of the displacement. And here this is work equal changing kinetic energy. The work done by the net force in moving a particle equals increment in its kinetic energy. And the increment of kinetic energy of particle depends on the initial and final state of the motion, while the work depends on the value of the force along the path followed. And it should be noted that value of the kinetic energy depends also in choose of internal initial reference frame. Okay, and the potential energy. Potential kinetic energy may be only positively, but potential energy may be positively or negatively. In here, this is figure graph Y versus X. Now consider U and the U's to be in the two particle systems. When the ski lift rises, you to the top of the hill, it is downward mgh, and mgh on the system. This work stores the potential energy of the systems. In here, this is pass number 1, and from 1 to the 2, and the path number B is following, and from 2 to 1 in here. And potential energy function. We know, and the work done by the conservative force on the particle does not dependent on the path. Does not dependent on the path. It can depend only endpoints 1 and 2. We use the property to define potential energy function U, and here that is associated with the conservative force. And when the car skids down the hill, the work done by the gravity decreases the potential energy of the systems. In general, and here we define the potential energy function such as the work done by the conservative force equal the decrease in the potential energy function, and work equal minus changing potential energy. This is in here. This is notation, not the notation potential energy. Even now, and the definition potential energy function and changing potential energy, the second potential energy minus first potential energy, and replace it minus and integral from S1 to S second, and force multiplied by displacement. And the third equation, law of conservation of energy. We know, and the mechanical energy, and the total energy of the particle, and here this is kinetic energy plus potential energy. And to replace kinetic energy mv square divided by 2 plus potential energy. But we assume the only conservative force act on the particle. If we obtain and changing kinetic energy plus changing potential energy is equal and 0. And therefore, the total energy of a particle on which only conservative force act remains constant with respect to initial reference frame. And total energy equal kinetic energy plus potential energy equals the constant. And the constant. If we know, and this statement is called law of conservation energy of the law of the particle. In other words, during motion under conservative force, both kinetic energy and potential energy may vary, but always in such way that if one form of the energy increases, another one decreases by the same amount. With this here, the continuous exchange of kinetic energy and potential energy. Maybe the law of conservation energy of the particle on one hand and consequence of the law of motion, and on the other is a special case of more general law of the nature, the law of conservation energy. In here, today we studied and the physical term and power, work, energy and power. we now and work and will be in the and equal and changing kinetic energy when and moved in the body, and the second and work equal as the changing potential energy, and the final and the law of conservation energy, and the statement that this is formula, and here this is law of conservation energy, and the law of conservation energy and the law of motion one hand, and the other and special case of more general law of nature in here. Thank you for attention.